today is called the acid-base properties of salts. Salts, which are ionic compounds, salts that consist of the cations of strong bases and the anions of strong acids have no effect on hydrogen ion when they are dissolved in water. Okay, why is that the case? Well, for instance, HCl is a strong acid. In water, this is a one-sided arrow. And the hydrogen and chloride ions completely dissociate, and we never have the reverse reaction. Meaning that once we've got chloride dissolved in water, it has no affinity for hydrogen ion whatsoever. They will never rejoin and go back in the reverse direction. Chloride does not have an affinity for the hydrogen, or we could think of it the other way around. The hydrogen has no affinity for the chloride in an aqueous solution. The other way around, let's look at a strong base, KOH. When it dissociates, it's got potassium and hydroxide, and again, this never goes back. It never goes in reverse. Potassium, along with hydroxide, they have no affinity back for one another. Okay, so if you've got a salt that is made up of the cation of a strong base and the anion of a strong acid, it's not going to affect pH. So what are some examples of that? Oh, well, let's use this one. Let's say potassium chloride. That's an example of a salt that would have no effect on the pH of a solution. You just check the pH of sodium chloride in lab, and that as well should have been a neutral solution. Okay, so these are neutral pH 7 solutions. They don't change the pH of water when they're dissolved in them. What's another example? Let's use, how about lithium nitrate? Okay, cation of a strong base, anion of a strong acid. You dissolve lithium nitrate in water, it's not going to change the pH of the solution. The pH will stay neutral. Okay, so what kinds of salts do have an effect on the pH of a solution? Well, let's just see. Acidic solutions. What kinds of salts give us acidic solutions? Well, we are going to have salts, for instance, where the cation is the conjugate acid of a weak base, and the anion is neutral. And when I say neutral, I mean that it is the anion of a strong acid. An anion of a strong acid is neutral. Okay, the cation would be the conjugate acid of a weak base. So what would be an example of a salt whose cation is the conjugate acid of a weak base and its anion is neutral? Something like ammonium chloride. And if you look back at your pH data from class, you should see that ammonium chloride indeed was an acidic solution. Okay, why is it an acidic solution? When this thing dissociates, chloride is going to do nothing, but ammonium, because it's the conjugate acid of the weak base ammonia, what will it do with one of its hydrogens here? It will give it off into solution and make the solution acidic. Okay, what kind of salts give us a basic solution? Do you have to memorize these? Yes, you do. So the cation is neutral. That means that the cation is the cation of a strong base. Essentially, you guys, it's going to be group 1 metals. Group 1 metals. And the anion is the conjugate base of a weak acid. So what is an example of this? Let's use a different color. Let's use orange. No, I don't want to do that. For instance, the cation is neutral. So let's say sodium, okay, because that is the cation of a strong base, sodium hydroxide. And the anion is the conjugate base of a weak acid. Oh, well, let's do the one that you did in lab. Acetate, C2H3O2. The sodium, because the cation is the cation of a strong base, and it's a strong base because it has no affinity for hydroxide in solution, okay, this is going to be neutral. But this acetate ion is the conjugate base of the weak acid, acetic acid. And so this ion, acetate, now has the ability to do what? It has the ability to accept a proton, accept a hydrogen ion, accept a proton from water. So it takes a proton from water, leaving hydroxide in solution, making the solution basic. Okay, you have to learn these things, because now we're going to do a problem about finding the pH of a salt solution. All right, so calculate the pH of a 0.30 molar sodium fluoride solution. Okay, so this is a salt solution. It's a sodium fluoride salt solution, and we want to calculate the pH of that solution. And we're also given in the problem the Ka for hydrofluoric is 7.2 times 10 to the minus 4th. Okay, so what we're going to do right now is going to be extremely complicated. It's hard. That's just how it is. Okay, so the first thing that we need to do with the salt problem, and it's really important with the salt problem, is what is in solution? What are the major species that are in solution here? So, major species okay, so what do we have? What do we have in a beaker of 0.3 molar sodium fluoride? Well, we've got water. Now, if it's a solution, that means that it's dissolved. Besides that, it's a group 1 metal, so it's always soluble. So we've got sodium, and we have fluoride. All right, now, what is going to affect the pH of this solution? If it was just water, it would be pH 7. If this was a salt that consisted of the cation of a strong base and an anion of a strong acid, it would just be neutral. It would be 7. Okay, but it's not, or we wouldn't be doing the salt problem. Okay, so which of these things, the sodium or the fluoride, is going to affect the pH? Well, the sodium is the cation of a strong base. It has no effect on pH. But fluoride, on the other hand, is the anion of a weak acid. It is the conjugate base of the weak acid HF. Oh, hey, look, what a hint. What a hint. You're given the Ka for HF in the problem. That could help in kind of determining things as well. Okay, so the conjugate base of the weak acid hydrofluoric. So this, right here, this fluoride ion is going to be the one that affects the pH. Okay, so that's the first step, figuring out what is going to affect the pH in the solution when we're talking about salts. So it's going to be the fluoride. So the next thing we need to do is we need to figure out what is the fluoride going to do. Well, let's just write down here that the fluoride is the conjugate base of HF. And the reason that we're writing it down is because now we have to write a reaction that shows us what the fluoride is going to do in solution, with water. And this is my key. It's going to act like a base. So, weak bases react with water. So let's write this thing. Fluoride, which is aqueous, is going to react with water. It's going to give us HF. And what else is it going to give us? Okay, so first of all we figure out what it is that's going to affect the pH, and then we write the reaction for how it's going to affect pH. If it was the opposite, you guys, if this was ammonium, it would be a conjugate acid dissociation giving off hydrogen ion in solution. Okay, so here it is. Now, what are we trying to do here? We're trying to find the pH. What do we have? Well, we've got hydroxide. So, you know, that's going to help, right? That's going to get us there. So, plus water. That's AQ. That's liquid. This is going to be HF, aqueous. Okay, so hopefully by looking at this thing, you guys can figure out how we're going to get to the hydrogen ion concentration. So now, you know, of course, we want the hydrogen ion concentration at equilibrium. So we've dissolved this salt, it's reached equilibrium. The fluoride's reacted with the water, now it's in equilibrium like this. So the reactant and product concentrations are constant. So let's go ahead and write an equilibrium expression for this thing. So our equilibrium expression is going to look like this. K, what is this? Is this a Ka or a Kb? Well, it's a Kb because the fluoride is behaving like a base, right? It is picking up a hydrogen ion from water to make hydrofluoric and hydroxide. So this is a Kb, HF, OH minus, okay, there it is. So let's set up an ice diagram. It's a liquid, I'm getting rid of it. What is my concentration of fluoride initially? Oh, I don't need to do that. I'm getting rid of this. And how much HF do I have initially? None. And none. I'm going to lose X. I'm going to gain X. Gain X. 0.3 minus X. 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 So what do I do next? Well, I'm going to plug into my equilibrium expression. But in the problem, I given a Kb? No, I'm not given a Kb. What am I given in the problem? I'm given a Ka for hydrofluoric acid. But this isn't a Ka problem. This is a Kb problem. So now we've got a problem with our K. So what are we going to do? Well, we're going to do this. We're going to say that Kb is equal to Kw divided by Ka. Okay, so this is a relationship that you have not seen yet. The Ka of a weak acid multiplied by the Kb of its conjugate base always gives you Kw, and vice versa. So, if we're given Ka, we know Kw, we can calculate the Kb for the conjugate base of that weak acid. So, our Kb is equal to 1.0 times 10 to the minus 14 divided by, what was our Ka? 7.2 times 10 to the minus 4. So our Kb is equal to 1.4 times 10 to the minus 11th. Excellent. Now we've got our Kb. Kw of water, Ka for hydrofluoric. So now let's plug into our equilibrium expression. So that's going to be 1.4, plugging in. 1.4 times 10 to the minus 11 is equal to x squared over, what am I going to do with that? Goodbye. 0.30. So that should give me an x value of 2.0 times 10 to the minus 6. What is the identity of x? Hydrofluoric and hydroxide. Oh boy. So we're almost there. We're almost done with this problem. So now that we know the hydroxide ion concentration, what are we going to do? Well, we can do one of two things. We can use hydrogen ion times hydroxide ion equals 1.0 times 10 to the minus 14. We could do it that way. We could find POH, and from POH we'll subtract from 14 and that'll give us the pH. That's the way I want to do it. So that you guys should check this. Part divided by the whole to make sure that I'm okay percent dissociation wise. Make sure I'm 5% or less. Okay, and so the POH is equal to the negative log of 2.0 times 10 to the minus 6. And so POH is going to be equal to 5.69. But we're still not done with this problem. Okay, so we're almost there. I'm going to take 14.00 minus 5.69, and we're going to get 143.8. Is it acidic or basic? It's basic. It should be. It's a Kb. This is the conjugate base of a weak acid. It's making a basic solution, drawing hydrogen ion out of the solution. Ooh. It's going to be a fun problem set. And you're going to see it on the AP exam, I guarantee it.